Okay. Hello, everyone. Welcome to discussion 8. Well, today we will review group delay, phase delay, these two very important concepts, and then also the significance of linear phase property. Okay, and then we'll move on to know how to determine if it is a linear phase sequence. Yes, I'll try to make it organized, and then we'll strengthen our understanding with exercises. Okay. So the first section is review. Okay. So group delay and phase delay. They're just different names for the equations, and we need to remember that the group delayed is basically the differentiation of our phase response with respect to the omega, right? And we have a negative side here. And in the graph, it can be interpreted as the local slope. Of course, the negative local slope, right? And for the phase delay, it is basically the phase response over omega. And it can be interpreted as the slope from a single point to the origin. Okay, and if I plug it out, the phase just go down from 0, and we can see that the phase delay always corresponds to the slope from a point to the origin, right? Of course, you need to take the negative part, the value is the slope from this point to the origin. And for the group delay, it is local, the local slope, okay? So this is a difference. And you'll see that when it is linear across in the origin, the local slope is identical to the slope from the point to the origin, right? And if it is linear, affine, I mean, if it is affine, you'll see that, okay, the phase delay now will change depending on the omega, but the local slope will always remain a constant, okay? Cool. So based on these two concepts, we introduced phase, linear phase. Okay. To be more general, we can say it is a affine phase. So it should be in the form as R-var omega plus beta, where R-var and beta are constants. Okay. So if the beta equals to 0, we know that, okay, we only have R-var omega left. And it is sometimes written as omega d. Okay, so the d is a delay. Now the concepts become consistent. And how to determine if a filter has linear phase? So the only criterion is the tau g of omega, which is a group phase, should be constant. Okay, cool. Any question about that? Oh, okay, no problem. You're awesome. Okay, so our next question is how to determine if a filter has a linear phase property. How to determine given n h of n. Okay, so the method 1 is to calculate the phase response. Okay, so in the previous homework, we were asked to calculate the phase response and magnitude response, right? So they are both frequency response. So traditionally, we can get our phase response and observe if it is in the form of a real value, and then E, J, theta, omega, and So this is basically the phase response, and we can observe if the phase response is in the form of an affine function. Okay, but sometimes we have other methods. So here comes our method 2. It is to just observe the edge of n itself. Okay, because we are given the edge of n, right? So it takes some time to calculate the edge of omega, the dt of t. If we can know if it is linear by only observing the edge n, it would be great, right? So given the edge of n, we can first conclude if it is IIR or FIR, right? The IIR is infinite and the FIR is finite, okay? So it is pretty easy to determine if it is finite or infinite. For example, you're given an edge of n like this, and it is 0 except for these supporting points, okay? So we can easily tell, oh, it is a finite one, right? And we have an important conclusion, which is the IIR can never has linear phase if it is causal and stable. And usually we want a filter to be causal and stable, right? And given this prerequisite, IIR can never have linear phase. So usually what we have is FIR. And given an FIR, which is finite impulse response, or we can say it's a finite f of h of n, we just need to observe if it is symmetric or anti-symmetric. The thing to be careful about is the concept anti-symmetric doesn't mean that, oh, it is not symmetric, so it is anti-symmetric. No, it also has strict relationship, which is basically h of n equals to minus h of n minus n, where n is the length of the finite h of n. And given that it is symmetric over anti-symmetric or symmetric by origin. So if we have a delay, we just need to shift it. But here, for simplicity, we're defining, we define them given that they're symmetric by origin. And if it is symmetric, we don't have the negative side. Sorry, my alarm clock. Okay. Well, everyone know I get up late now. Ooh. Let's see. So the way to think is very clear. First, we get an edge of n, and then we determine that it is finite or infinite. If it is infinite, we can just throw it away. If it is finite, we can further observe it is symmetric or anti-symmetric or nothing. If it is neither symmetric or anti-symmetric, it can't have linear phase, okay? If it is symmetric or anti-symmetric, we can ensure that this FIR has linear phase. So we like both of them, okay? And someone will ask, what about the restriction, right? So in the lecture, there is a table containing 4 types of the FIRs, and there's 2 columns called restrictions, right? Like the value at omega equals to 0 or pi, right? What about this? So the idea behind that is the restriction on these values are just the result of the even or odd properties and anti or non-anti-symmetric properties. So it is just a result of the properties of your sequence, and it doesn't matter what the values of your hn is, okay? So if we are already given the h of n, we don't need to consider the restriction, because given the h of n, we only need to look up the table and know the conclusion. So it is like a conclusion or result. They're basically some mathematical expressions, and you'll find out that, for type blah, 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 it has to be blah, 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 because they canceled out or something. Or the cosine is always 0, something like that. Okay, so when should we be careful about the restrictions. So if we need to design the h of n ourselves, so now we are not given an h of n. We need to design our own h of n. In this case, now we can choose which type of FIR we want, right? So now we have to consider, do we want to design a high pass, low pass filter, or any other characteristics? And combining these requirements, we can further look at the restriction to find the one that is most suitable. Okay. Any question regarding that? Wow, you follow so well. Great. So now we will move to the second section, which is exercises. And I hope you'll be happy with it. We'll check your understandings over the points just now. So let me write down the question. Now we have the FIR filter, and we know that it is real and causal. Okay? And we know that it is anti-symmetric or symmetric. We don't know which one it is, but it belongs these two categories. All right. So what can we know given only this line of information? Any guess? Any conclusion?
Phase.
Yeah. Thanks, Alice. So given it is FIR, and given it has this property, symmetric or anti-symmetric properties, we can conclude that, oh, it is linear. It has linear phase, right? So determining if it is linear is just so easy. Okay, you don't even need to calculate. But that is not the end of my question. So now I know there is 1, 0 at this point. Let's name this point A equals to 1/2 times E j to the j, a quarter of pi. Okay, so someone tell you they know 1, 0 at this point, and we don't know the numbers of the zeros, we don't know other zeros, and okay, and we also know the energy of h of n is 1. What does it mean? It basically means the sum of the square of the magnitude from or valid n, okay, equals to 1. Cool. And here comes my question. What is the smallest numbers of zeros in h of z? Any clue? Any guess?
Since I think it's because it's real, I think you have to at least include the conjugate of the given 0.
Very, very reasonable guess. Thanks, Edward. Let me write down the answer. Black color. So because it's real value, we know that each h of n is real value, the h of z will have conjugate 0. Okay, so we have a. We should also have a conjugate, right? Which should be j to the minus pi over 4. Okay, what else? Or this one, the other zeros, they use the property of the symmetric filter. So if you can recall, there is an equation derived from extracting some components from the Z transform. So it looks like this. Do you have any impression on this? And the plus minus here comes from symmetric or anti-symmetric filter. Okay, so what does it mean here? It means that if we take all the things on the right as a whole expression, the left-hand side and the right-hand side, they should have the same values given the same Z, right? So let's write it down as, for example, G of D. Okay, so you see that H of D and G of D, they should have the same zeros, right? Why is that? Because 0 is basically the values where the whole expression will become 0. Okay, so if A is 0, that means H of D when D equals to A should be 0. And because you have the equation here, we know that G D when D equals to A should also be 0, correct? And if we write the expression in the middle, we'll see that the G D equals to A is basically plus minus A minus N, the minus N H A to the minus 1 as a variable of H, right? And we know that this is 0. Okay, and here A is not 0, so we know that H of A to the minus 1 equals to 0, right? Here it comes a conclusion. For the symmetric filter, if A is 0, the A to the minus 1, or we say 1 over A, is also its 0, right? So now we can further derive A minus 1, right? And they are conjugate, so we also have A minus 1 conjugates. Wow. So 1 over A is basically 2E minus J pi over 4. And its conjugate should be 2E to the J pi over 4. Correct? Now we are very happy. We have got 4 zeros. And we can't derive any more zeros given this limited information. So we can answer the question earlier. What is a small number of zeros in H of D? It should be 4. Ooh. So we solved this problem. And then I will ask, can you write down H of N? Any random guess or reasonable guess, of course.
How did you get the 4 zeros?
Hi, Emia. So you know that we are given the first zeros, right?
Mm-hmm.
And then we know that it has to have a conjugate, so we get 2 zeros.
Oh, okay.
Yeah, and then given these properties, this property is derived from the symmetric filter. Given this property, we know that when when A is 0, 1 over A should also be a 0. So we get the third 0. And then it also has to be conjugate. So we have the fourth.
Okay, thank you.
You're welcome. You give me a chance to give a high level conclusion. Thank you. And my next question is, can you write down H of N? And if you can, of course, you need to write down the H of N. So let's see what we have done up to now. So we are given a 0. We're given the energy of H of N. And now we have concluded the 4 zeros that must exist. Okay. So let's say if we know that the H of 0 is actually 4. So here we see it is smallest number of zeros, right? It can have even more if it gives us another zero, other clues, okay? But given this limited information, we know that the smallest number of 0 is 4. And let's say if we know that the number of 0 is exactly 4, can you write down the H of N? Now the question becomes more strict. So yeah, I know it's hard. So let's try to continue with our 4 zeros and to see what we can discover. Okay, we know that H of D, given the fact that it is finite impulse response, it should be written down in the form of the multiplications of zeros, right? It does not have poles, so the denominator should be 1, or you can say it does not have denominator. Okay, and usually we have a game here, which is a constant. Okay, I used G before, so let's change another letter. Let's say A. Okay. And what should be filled in? It should be in the form of 1 minus the zeros. Okay. 1 minus A over Z. And A is its first zero. Okay. And it is also more common to read read like this. It becomes familiar, right? And continuously can write out others. A minus 1, B minus 1, and A minus 1 star, B minus 1. Okay. So here we get the expression of H of D. All right.
Can you repeat why the poles again?
Because it is a finite infinite response. So for the FIR filter, it does not have the denominator part.
Oh yeah, thank you.
Great. And then what is the H of D? So the H of D is basically the Z transform, right? The transform, let's say it starts from 0 and goes to n because it is causal and finite, right? The n is the length of the filter. And it should be like this, right? And you'll see that if you expand it, it should look like H of 0 times 1, and H of 1 times Z to the minus 1, and H of 2 times Z to the minus 2, blah, 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 right? Therefore, if you expand this expression, you'll be able to write it in this form, right? Something plus something times Z to the minus 1 plus something to the Z minus 2. And then you'll be able to match the H of 1, 2, 3, 4, and then you'll get your H of n expression, all right? And let's do it now. To save you times, I calculated beforehand, and you can check it. So let's substitute the A values here. So we already know all the concrete values of all the zeros, right? So we just need to substitute it and be patient, and we'll get something like this: 1 minus 5 square root 2 over 2. All right. So we'll be happy to see they are in the same format. Okay. Therefore, we know that H of 0 should be A. H of 1 should be A times 5 square root of 2 over 2. Okay. A times 4. A times minus A times 1, which is A, right? Great. So let's review the question. The question said that the energy of Hn is 1, right? And here we can express H of n or in terms of A. There's only one unknown variable, right? So by applying these constraints, we can calculate the A values, right? I'll tell you the value is 0.123. It is really not easy to calculate, but it's an example question. So we know H of n now, right? Our question is solved. And let's go back to C. At the beginning, we already know it is linear phase, right? Because it's symmetric or anti-symmetric, and it's a finite filter. Okay. And now, given the H of n, let's practice and to verify this. Okay. So you see that A and the A are symmetric, right? A at the terminals, and you notice that H of 1 and H of 3. Wait, did I do anything wrong? Oh, sorry. There is nothing wrong. I just copied them carelessly. There is a minus sign here, negative sign here. Okay, now they are symmetric, right? So from observing H of n, we can also know that it has a linear phase, right? And let me ask you the last question about this this context. So questions. What is a group delay? Wow, It is so intimidating. What is a group delay? So the group delay, tau g of omega, is a negative derivative. Okay, cool. Anyone? Oh, someone asked question in the chat box. Sorry, I'll answer them first. Arya said, why not z minus a? If you recall, when we write down the general form of h of z, it is b, the constant, times something z minus 1 times something until z to the minus m, right? And for the denominator, it also a plus something z to the minus 1 until z to the minus n, right? And if we have the denominator, we can times both of them by zm or zn, right? And then it will be turned into the form that we can factor into z minus something times the, right? But here we don't have the denominator, or we say the denominator is 1. So the all the things left should be a constant times something z minus 1 times something z minus 2 and times something z minus m. And they can be only factored into something like 1 over a z minus 1, blah, blah, blah. Okay, or the order of the won't match. Does it answer your questions? Cool. One writing it as if you pose at 0. Yes, you can say in that way. Yes, but so we'll say that even in that way, that is just a trivial pose, because you know the range of convergence, the ROC, should be going outwards from the outmost pole, and the pole is at 0, so we just need to remove the 0 from the ROC, and to all the other values, they are still consistent. Cool. Okay, so let's come. I recall someone unmuted themselves before. Please go ahead. Okay, it seems that it is resolved. Let's what? Okay, so let's discuss this question. What is a group delay? And I give you the expression here.
Yeah, I was wondering if this would, I don't know what constant, but since our phase is linear, the derivative is going to be like the negative of whatever like our slope, linear slope was. But
yeah, you're right.
Yeah,
you're right. And here I'll teach you a easy trick. So let's observe this this sequence. We'll notice that for a filter without phase delay, it should be symmetric over the origin, right? Like this. Okay, but now it is not 0 here. What it is? The center is 2, right? 0, 1, 2, 3, 4, and you see 2 is its center. So group delay is 2. And the other way to say that is n over 2, and we know that n here is 4, right? It goes from 0 to n, and n is 4. So it is 4 over 2, and it is 2. And someone will ask, how do you derive the n over 2 here? We don't even know the phi of omega, right? You see that the equation is very complex, and it looks hard to factor it in a form like something a real value times the e to the j phi omega, right? I don't know how to do this. How can you get the result? So let's do it more strictly mathematically. We know this property, right? And this property becomes important again. From the result, we know that it is symmetric. So the positive and negative value here will become positive because it is symmetric. Let's see how we can make use of this property. And let's make z equals to e to the j omega. So now the values are located on the unit circle, and we will get our DTFT. Right? So the h of z will become h of omega, and the z to the minus n will be the e to the j of omega n. Okay, so the z transform become the dt of t. Cool. And then we can write it as a multiplication of magnitude response and phase response. So it can be written as the magnitude response times phase response here. And on the right, can do, oh, sorry, there's a -1 here. No. It's not -1. Because z minus 1 is basically e to the minus j omega, right? So it will result in h of minus omega. Great. H of minus omega, and its phase response. Great. And we know that it is symmetric. Symmetric basically means h of omega equals to h of minus omega, right? And it basically means that this is what? This is symmetric as well, or not?
Oh, would this be anti-symmetric, the phase?
Yes, you're right. Cool. And then this will cancel out, right? And this term, we can rewrite it using this equation. Write it explicitly. What should it be? It should be minus j phi omega. Right? And I just can't stop myself moving this to the left. And we will get j to the 2 phi omega, right? Equals to e to the j minus j omega n. Wow. So the problem is solved. Woohoo. Correct? And then we do the differentiation. It's n over 2. Wow. So it matched the equation we used earlier, right? So you see, getting the group delay is not difficult at all. But notice that this equation is only for the symmetric, okay? If it is anti-symmetric, it will become negative side. So this is for positive. If negative, you can derive it after class. It should be k pi over 2, right? But the tau g omega will not change. The tau g omega will still be n over 2, right? But the phi of omega, sorry, I should use the same letter here. Cool.
Wait, sorry, in which case do you have the added k pi over 2? Is this?
Negative. So when it is positive, we get this. When it is positive, sorry, what? When it is positive, we get this result, and when it is negative, we get this result. Okay. So the process are similar. You just need to add another negative side, and you know the negative side will result in the pi. K pi.
When you say if it's negative, are you talking about h? Are you talking about like the z transform or the original h of n itself?
Okay. So negative means the original h of n is symmetric, because when it's symmetric, we have this. Okay. And negative means the original h of n is anti-symmetric, and the equation we use is minus to the minus n h of. Okay.
I see. Thanks.
Yeah, the difference comes from the very, very fundamental property of the symmetric and anti-symmetric. The h of n equals to h n minus n. If we think that d is 0. Okay, to help you better strengthen this concept, I will give you a very quick test, and then the discussion will end. Well, the drawing is ugly, but I'm sure you get it. So you see that the value of h1 of n is 1 at 0, 2, 2 at 1 to 3, and 1 at 4, right? So what can you conclude from this? Feel free to unmute when I'm drawing. Cool. So you see that it is symmetric, right? The h of 0 match h of d. The h of 2 may match h of 3. And this is the center. So we know that it is symmetric, but it is symmetric across 2. What does it mean? It means the delay is 2. Okay. And from the symmetric property, we know that it has a linear phase. And yeah, it is finite, right? It only has 5 supporting. Finite. And what about this one? Can anyone tell me what the phase should be?
Would this just be 0 phase?
Yeah, you're right. FIR, 0 phase. Which means that it will have no delay. And why don't people use the FIR with no delay?
It's not causal.
Yes, exactly. So you see that it starts from -2, -1, which means that, okay, it will use the future samples when you process the signal, and which is not causal. So we'll see. This is always preferable in practical system, real-time systems. Okay, and you see that the only difference between the linear phase FIR and the 0 phase FIR is the delay, the group delay, right? Wait, it is 2? Yeah, it is 2. And over 2, 2. So you notice that even though we have 5 supporting here, but because it starts from 0, the n is 4 instead of 5. Okay? So when we have when n equals to 4, we actually have n plus 1 supporting. So in the type table, in the FIR type table, also remember that, okay, when we say n is even, we actually have n plus 1 supporting, which means we have all supporting. And please remember to keep this correct when you're in the exam, or it will mess up your following results. But I'm sure anyone that attends my discussion will have no problems regarding that. Okay, so any question about anything?
So just to make sure, so the n that we use in like the capital N actually refers to like the index of the largest sample starting from 0 rather than actual like the number of samples, which would be n plus 1.
Yes, starts from 0, ends at n. And yes, you're right.
Okay, cool. Thank you.
Thank you. Thank you for a question. Someone asked in the chat box, okay, Amia asked, is H symmetric? Is H symmetric? Okay, that is a good question. So we need to review a important property, that is when the H of n is real and even, the H of omega is also real and even. So for the H of omega to be real, that means it has 0 phase. Okay, so you'll see that, wow, the H2, for example, the H2 of n is exactly real and even, right? So its H of the omega is also real and even, and we'll see that it has 0 phase and it is consistent. But the symmetric here, we have a looser definition here. You see that it is symmetric by 2, but we still say it is symmetric, right? But we can't say it is even because it is not. It does not match the definition of H of n equals to H of minus n, right? It does not stand. So we can't say the big H is even. As for okay, and you ask if is a big H symmetric. So if your definition of symmetric is H of n equals to, so I don't think it will stand because you know, when we define the symmetric property, we give H of n equals to H of n minus n, right? Or given the delay, we have H of d plus n equals to H d minus n, right? This is how we define the symmetric, but for H of omega, the variable is omega, and it is also a continuous variation across omega. So I don't think it stands. But Thank you for your question. It's very insightful.
So it's symmetric by Hermitian symmetry?
Oh, yes, that is. So if you ask Hermitian symmetric, h of n, if h of n is real, okay, we only know it is real, then the h of omega is Hermitian symmetric. In case someone forget the definition, the Hermitian symmetric basically means h of omega equals to h of minus omega, and this phase response is the opposite when we take a negative value. Okay. Do I answer your question? Cool. Thanks. Wow, you guys are really good at asking questions. Okay, that is the end of my discussion, and feel free to stay in the office hour. I will stop the recording.